Bismillahirrahmanirrahim. Here we are with our lecture number 9, design, and we have a design example. The problem states that design first order RC circuits using standard parts. The voltage across the capacitor is 50 minus 100 e raised to power minus 200t. So we have all the information hidden in this equation. So first of all, what we'll do, we will write an equation that is our general equation, that is Vc of t is equals to V of 0 negative, mean voltage across capacitor before switching, minus V of capacitor at time t is equals to infinity, such that e raised to power minus t over tau plus voltage at times t is equals to infinity. As we can see that there is one-to-one correspondence between these two factors. This 100t, 100 e raised to power minus 200t, that is correspond to this portion of our equation, and 50 is corresponding to v at infinity. So it is very obvious from our equation comparison that voltage across capacitor at times t is equals to infinity, that will be 50 volts, and similarly, we have voltage before switching 0 negative minus V at infinity, that is equals to minus 100 volts. This is obvious from this portion of the equation. So here we can calculate at V at time before switching. So this will be equals to 50 volts. So we have minus 50 volt. So we have calculated both of our numerical values. Now what next? We have to calculate the time period. So tau here is equals to 1 over 2000. That is obvious from our equation. This is basically 2000t, not 200t. So 1 over 2000, this will be equals to 500 microseconds. Similarly, we can have the value of RC. This is equals to tau, and this is equals to 500 microseconds. As the demand of the question doesn't telling me anything about the numerical value of resistor or capacitor, so it's up to me what values of resistor or capacitor I select. So I take randomly a value of R, that is 100 kilo ohms. So I can find out the value of C for this 100 k resistance such that the time constant will be 500 microseconds. So 500 into 10 raised to power minus 6 divided by 100 into 10 raised to power 3 in 100 kilo ohms. So that will be 5 picofarad. So this will be the capacitor, and this will be the resistor. If we connect both, such that the time will be 500 microseconds. Now what next? Now in our last step, we just need to make a circuit diagram such that at times t is equals to infinity, our voltage is 50 voltage. So it means that we will draw a voltage source such that its value will be 50 volts, and this will our RC circuit, this will be our R of 100 kilo ohms, and this will be our capacitor. Both are in series, so this will be our final value or steady state value when the voltage when the 5 picofarad is the capacity of the, and this will be the voltage across capacitor plus minus Vc of t. Similarly, this will be the time, and at time t is equals to 0, our switch will be connected to this terminal. Now, before switching, the voltage across capacitor was minus 50 volt. So it means that we have to connect a point such that its voltage will be minus 50. So negative terminal here, positive terminal here, and we will provide 50 volt, and we will connect with this point. So this is the complete circuit diagram, and this was the design value. So whenever you are given with this type of equation, so every information is written here. This is having no exponential included. This is the only numerical value showing you V at infinity, voltage across capacitor infinity. And whenever there is an exponential connected, multiplied with a numerical value, mean this term is basically telling you that it is the sum of both V naught, V at 0 negative, mean voltage before switching, and voltage at time t is equals to infinity. So just by comparing the equations, you can find out the circuit diagram. Now I have a next numerical. Okay, now we have another example. Here we can see that we have a circuit diagram having two voltage source. One is of 10 volt, the other one is again 10 volt. So before switching, the inductor was connected here, and after switching, the inductor new position will be at this point. So first of all, what we'll do, we want to calculate the time constant, and this will be equals to L over R Norton, R equivalent or R Norton, and there is only one inductor, so I will write only L here. So for time t greater than 0, greater than or equal to 0, your R equivalent, that will be, now in Norton equivalent, what we do, we just remove this inductor and open all the voltage source, short all the voltage source, and find out the equivalent diagram. So in this case, you can see that this 50 ohm resistor and this 25 ohm resistor, this will be in series, and that will be in parallel with this 50 ohm resistor. So I'm just writing R equivalent, that will be 50 ohm resistor, that will be in parallel with 75 ohms resistor. So very easy to calculate. What we'll do, 50 inverse plus 75 inverse and whole inverse. So this will be 30 ohm resistor. Now this is our Norton equivalent. Now time constant, inductor is already given. This is 150 into 10 raised to power minus 3 millihenry divided by 30. So our time constant will be 5 milliseconds. Now, in our next part, what we'll do, we need inductor points. Because this is an inductor diagram, inductor question. So we need the value of IL. So IL at time t is equals to 0 minus, before switching, that will that will be 100 or 10 divided by 50. It's very easy to calculate. We will short this inductor before at steady state values. At steady state, inductor act as a short circuit. So before switching, we are shorting this, and we will calculate this branch current. And our circuit is connected to this green portion here. So we are left with a very, let me draw this diagram very quickly. Plus minus 10 volt, and here we have 50 ohm resistor, and this is a short circuit. And you have a 50 ohm resistor and a 25 ohm resistor, and we want to calculate this branch current. This is IL. So this is very easy. What we do, 10 divided by uh, 50 ohms and 25 ohms. As you know that we have a short circuit parallel with 50 ohms and 25 ohms, so there is no purpose of this 50 ohms and 25 ohms. So all of the current will pass through this branch, and this is having 50 ohm resistor in series with 10 volts. So what IL at 0 negative, what will I get? That will be 0.2 ampere of the current. Similarly, we will calculate IL at time t is equals to infinity. Now at time t is equals to infinity, after switching, this voltage source will be cancelled out, and you are left with this voltage source. So again, that will be our short circuit, and both resistor 50 ohm and 25 ohms will be neglected, as there is a short circuit in parallel with the voltage source and the resistor. So we will be left with minus 10 10 divided by 50. So that will be equals to minus 0.2 ampere of the current. Now I have an inductor equation as always. So that is IL of t. This is equals to IL at times t is equals to infinity plus IL at 0 negative minus IL at times t is equals to infinity e raised to power minus t over tau. And we know the value of tau, and we know the value of IL infinity and IL 0 negative. So putting all the values, that will be minus 0.2 plus 0.2 minus minus 0.2 e raised to power minus t over 0.005. So that comes out to be minus 0.2 plus 0.4 e raised to power minus 200t, and that is in amperes. Now, demand of the question is to find out V naught. Now, here is V naught. This is the V naught. This we want to calculate. So let's calculate this thing. Now, here you can see that your V naught is basically, let me, no, this is a voltage. Let's say I say this voltage as VL, because this is the voltage across this inductor, and this voltage, we say that this is our source voltage, and I say this is a source voltage. Once we calculate the value of VL, we can easily calculate the value of V naught, because V naught is basically equals to 25 divided by 50 plus 25 multiplied by this VL. So this will be equals to VL divided by 3. So I will keep this thing in our mind. Now, in proceeding, let's do the node analysis on these equations. Okay, let me make quickly equations here, because whenever I go to next page, this diagram will be gone. So again, I have VLT minus VS divided by 50 plus IL. What I'm doing, I am this current plus this current is equals to 0. So this current is basically IL, and this current is VL minus VS, mean this VL minus VS, and the other one is VL plus VL divided by 75 equals to 0. Now rest of things are just numerical calculations. So VL divided by 50 plus 10 over 50, this is equals to VS, and VS was minus 10, plus 0.4 e raised to power minus 200t minus 0.2 plus VL divided by 75 equals to 0. Now here, by doing all the numerical values, voltage across inductor VL, function of time, that will be equals to minus 12 e raised to power minus 200t. I am skipping all the numerical steps, but you can calculate it. So V naught was equals to VLT divided by 3. So what will be our V naught? That will be equals to minus 4 e raised to power minus 200t volts. So that's how you will perform all the numericals. These are very easy to calculate, all the numericals, and the method is same. In preceding lectures, a new topic is starting, and that is very interesting and a bit tough one. So stay tuned, and Listen very carefully. Thank you very much.